Here we go, last topic, integration by partial fractions. We're looking at the second part of this, but I'll bring in some stuff from the first lesson that we had before. So here's our first integration question, and because we're talking partial fractions, maybe we're going to approach it that way. So we understand that when we do partial fractions from before, the first thing we do is rewrite the equation or the question, factoring the denominator, and making sure that we've got a higher degree in the denominator than in the numerator. I see the degree in the denominator is 2 and the degree in the numerator is 1. That's the biggest exponent on any variable, so we are good to go ahead. I factor out an x from the denominator. I'm going to have x onto x plus 4. So when we break this into partial fractions, we're trying to find things that are easier to integrate for us. So we're going to rewrite x plus 2 over x onto x plus 4 as the sum of two partial fractions. We just have to figure out what those are going to be. So we take x plus 2 over x onto x plus 4, and we're going to write it as something over that x piece plus something over the x plus 4 piece. Now, of course, we know that if we wanted to clear the fractions in this, get rid of them, we would just make sure that everything is over the common denominator, x onto x plus 4. So the x plus 2 is fine. You can drop the denominator. In order to make the a over x onto x plus 4, I need to multiply in the x plus 4. And in order to make b over x onto x plus 4, I need to multiply in that x. Okay. Now we're just picking values that make our life easy. So if x was negative 4, and we just do the math, we're going to get negative 4 plus 2 equals negative 4 plus 4 onto a plus negative 4 onto b. So essentially, we're going to get negative 2 equals 0a plus negative 4b. So I can just drop that right away, which means b must be equal to 1/2. Likewise, if I say that x is equal to something that'll make the b term disappear, x is equal to 0, I'm going to have 0 plus 2 equals 0 plus 4a plus 0b. In other words, 2 is equal to 4a, and a is also equal to 1/2. Okay, so instead of integrating this hot mess, which I could totally have done using substitution, and it actually would have been an easier option, I'm going to now deal with the integral of a over x. So I have 1/2 over x. So I'm going to kick out 1/2 out, and then I'm just going to have dx over x plus, for b, I also have b is equal to 1/2. So I'm going to kick it out, dx over x plus 4. These are just u to the negative 1 integrations. So we're going to have 1/2 ln of x plus 1/2, ln of x plus 4. Ran out of room. We can combine these two things into 1/2 ln of x onto x plus 4, should we care to. And we put in our plus c. There we go. As an alternative, I totally could have looked at this problem and said u was equal to x squared plus 4x, which means du dx, substitution style, is 2x plus 4, which means that du over 2 is x plus 2 dx. And there we have a beautiful substitution, and we would get to the same place, but a lot quicker. The question always is, when should we use partial fractions? So first of all, you're going to have a rational expression, which is an algebraic fraction. So x dxx something over x dxx something else, right? And we want to get to the point for this level. We're just going to work on problems where the degree of the numerator is less than the degree of the denominator. So you could have like up to an x cubed in the denominator, but you wouldn't have x to the power of 4 then. The rational expression, so the thing you're integrating, cannot be made into du over u. Now, you can still use partial fractions. Our previous example, absolutely, we had du over u, and we did use partial fractions. It's just a lot more work for us. And the other thing for us, in this course, we're only going to deal with linear factors in the denominator. So things like x, or the binomials x plus 7, 2x minus 5. No x squared plus 13 or anything like that. That cannot be factored down into linear pieces. All right, we're going to get a few more examples under our belt. So we look at this bad Larry, and obviously the first thing we're going to do, check that it looks good for partial fractions, that it's certainly not going to turn, I don't think, into a du over u situation. So I'm going to write 7 minus x brackets dx, and I'm going to factor the denominator. So we can go x plus 2 onto x minus 1, which tells me that I could break this into partial fractions having a over x plus 2 plus some number b over x minus 1. All right, same thing as before. We're going to take whatever we can do to make this a single line with no fractions in it. So I'm going to multiply the 7 minus x is all good. It's already over the common denominator. I multiply x minus 1 times a, so I can drop the fraction, and I multiply x plus 2 times b. And if you don't know what I'm doing here, all the way back to your level 1 course, the video algebra basics, I believe. All the way back to the algebra basics videos. Okay, here we go. So we're picking values that are going to make our life easy. So I look at my first thing going on here, and if x was 1, I know that I'll get 0a. So I have 7 minus 1 equals, and I know right away I'll have 0a equals 3b. So I'm going to have 6 equals 3b. b must be 6 over 3. b equals 2. Fantastic. Another thing I could do is I could set x equal to negative 2, because then I'll have 0b. So I have 7 minus minus 2 equals negative 2 minus 1 is negative 3a. So I have 9 equals negative 3a. A must be equal to negative 3. So there they are, b and a. So I go back up. I'm going to change this integration now. So I will have, and maybe I'll switch colors and stay down on the bottom. So in this little box here, we're going to have the integral of a over x plus 2. So we're going to kick out a, which is negative 3, onto dx over x plus 2. And using the rules of calculus, we can make this into 2 integrations and just add them together, kicking out the b, which is 2 dx over x minus 1. Now, of course, this is a u to the negative 1, so every time we do these ones, we end up with the lns. Negative 3 ln x plus 2 plus 2 ln x minus 1 plus c. And done. Yes, you can bring things in and make very fancy pants kind of combinations, but this is good enough for me. Okay, that was just a really quick background, because what we're supposed to be working on in this one is the repeating linear fractions. So when we think about repeating linear fractions, what does that mean? That means if I had something, number, non-repeating means no matter what you had, x plus 7, 2x minus 15, and on and on and on, you never have, 2x plus 15, you would never have a repeated factor. So you would never get anything the same. If I had the same kind of situation, number, and it was over x squared onto x plus 7 to the power of 3, x squared is a repeating linear factor because it's x, right? It's x 2 times. X plus 7 is a repeating linear fraction because it occurs 3 times. So we have x plus 7 times x plus 7, and then once again times x plus 7. What does this mean? We just have to do a little bit of extra work, of course. So here's how it's going to play out. We're going to factor it. This one's already factored. That's great. And we're going to do what we always do. We start with the 1 over x minus 2 squared. We want to make it a sum of partial fractions. Any linear non-repeating one, like the x is fine. We just go a over x plus b. And we're going to do b over x minus 2 to the power of 1. Then we're going to do c over x minus 2 to the power of 2. And we would continue doing that, d over x minus 2 to the power of 3 if we had it, so on and so forth. A little more complicated when you use the lowest common denominator. Make sure you don't do something you shouldn't. So we're going to start with 1 equals, a has an x, but it needs x minus 2 squared. So we put x minus 2 squared onto a. B has a single x minus 2. It needs another one as well as the x. So x onto x minus 2b. And C has all the binomials but just needs an x. Okay, continuing on, same thing. Do what makes your life easier. I'm going to say x is equal to 2. That gives me equation 1 equals 0a plus 0b plus 2c. And there we go. C must be 1/2. Now let's say x is going to be equal to 0 and see what that clears for us. 1 is equal to negative 2 squared for a plus 0 times something, b is gone, plus 0 times c, c is gone. So a is equal to 1/4. There's no other handy, quick value that will work for us. You can pick any other value of x. I usually like the number 1 or minus 1. So let's say x is equal to 1. Our equation becomes 1 equals, and then we have 1 minus 2, which is negative 1. We square it, so that's 1a, or just a. And we have 1 times 1 minus 2, 1 times minus 2 times b, 1 times minus 1 times b, so that's basically like negative 1b, so a minus b, and then 1c, so a minus b plus c. We have 2 of these values already, so we can rewrite this equation as 1 equals 1/4 minus b plus c, and I'm going to write c as 2 over 4 because it's easier to combine my fractions. So there's plus c, that 1/2. So 1 equals basically 3/4 minus b. So 1 minus 3/4 equals negative b. That means b must be equal to negative 1/4. Follow the math, it works out. Okay, let's take it over to some integration. A little bit of a trick with this one. First things first, we have a, which is 1/4. We kick it out. 1/4 times the integral of dx over x. And then we have b, which is minus 1/4. Minus 1/4 times the integral of dx over x minus 2. And then we have c, which is 1/2, plus 1/2. And notice how I write this. Times x minus 2 to the power of negative 2 dx. Why did I do that? Because this is not a u to the negative 1 situation. We're basically going to be doing this, which we know from the power rule is negative u to the negative 1. You go up n plus 1 and you divide by n plus 1. And in this case, n plus 1 would be negative 1. Okay, so be careful. As we continue, ln x minus 1/4 ln x minus 2, and then we take this negative u to the negative 1 in fact, and we're going to minus 1/2 onto x minus 2 to the negative 1. There'll be a plus c in there, but I need to do a bit more work. I'm going to clean it up a bit just to make it shorter. 1/4 ln x over x minus 2 we have 1 over 2 onto x minus 2. And then we can fit our plus c in. Beautiful. Here we go again. Let's factor. We've got 1 over x cubed plus x squared, which is the same as when we factor out an x squared onto x plus 1. So we have a repeated factor of x and then a non-repeating factor x plus 1. That's fine. So we're going to deal with the a over the single x. And remember, we get a partial fraction for each iteration, each exponent up to the top one, and then x plus 1 on its own. Once again, we clear the fractions. 1 is equal to a has an x, it needs another one, and the x plus 1. B just needs the x plus 1. And c just needs the x squared. Okay, let's make x equals 0, which means we'll end up with 1 equals 1b. So nice. B is equal to 1. Let's make x negative 1. We have 1 equals 0a plus 0b plus 1c. c equals 1. Okay. We need another value. Let's make x into plain old 1. I should have, hold on, I'm going to erase this because it just looked like x minus 1, which is totally weird. So let's try that again. X equals negative 1. And now we're going to do x equals 1. So we're going to have 1 equals 1 times 1 plus 1 is 2. So we're going to have 2a plus 2b plus 1 squared c. But we already have values for b and c, so we can rewrite this as 1 equals 2a plus 2 times 1 plus 2 plus 1. Okay, so we have, moving the 1 and the 2 over, the 3 over to the other side, 1 minus 3, negative 2 equals 2a. Look at that. A was equal to negative 1. Here we go. Can I fit it on this side? I'm going to try for it. So we're going to have the integral dx over x plus b was equal to 1 as well. The integral of x in the negative 2, careful, dx, and c was 1. The integral of dx over x plus 1. Just rewriting so it tells me what to do. Negative ln x minus 1 over x plus ln of x plus 1 plus c, fine as is, or if you wanted to combine them using the logarithm laws, you'd have x plus 1 over x minus 1 over x plus c. Done and done. We'll finish this one and leave the really crappy ones for class. Yay! So here we go. We've got x minus 8, and we're going to do a little factoring on the bottom, 100%. We take out an x. That's going to leave me with x squared minus 4x plus 4, which I can factor into x minus 2 squared. Okay, so we know we're going to have something over x plus something over x minus 2, and then because of the repeat, we also have something over x minus 2 squared. I like to use these not too torturous numbers. Okay, x minus 8 has to be equal to, a is only missing x minus 2 squared, plus x onto x minus 2b, will clear that fraction, plus xc. Excellent. See what I did there? Let's go x equals 0. That means our equation will become 0 minus 8 equals 4a plus 0b plus 0c. So a must be equal to negative 2. Let's make x into positive 2. So we have 2 minus 8 is minus 6. 0a, 0b, 2c. c must be equal to negative 3. And finally, we're going to pick whatever you want. I'm going to pick x equals 1, just for the heck of it. So I get 1 minus 8 is negative 7. 1 minus 2 is 1 squared, so I get a. And then 1 times negative 1, so a minus b, and then plus c. So picking those values that make your life easier. Okay, sub in what we already know. Negative 2 is a, b is something, c is minus 3. So we have negative 5 already. In order for this to be true, b must be equal to 2. Okay, let's go with the integration in another color. A was equal to negative 2. We kick it out. Get ready for that law integration. B was equal to 2. We kick it out. And C was equal to negative 3. We kick it out. And we recognize that this is x minus 2 to the power of negative 2 dx. A little different. Okay, negative 2 ln x plus 2 ln x minus 2. And then we're going to have negative 3, but it's also going to be multiplied by the negative x minus 2 to the power of negative 1. So it's going to become plus 3 over x minus 2 plus c. Done. And like I said, I'll leave the terrible ones for later for class when we can all sit and stare at them and cry. But, you know, they follow the basic idea. You can solve them.